A plank of length 12 leans against a wall. Initially it is in vertical position and then it starts to slip down without friction. We have to show that the top of the plank loses contact with the wall when it is at 2/3 of initial height. Now suppose the coordinates of center of mass are x comma y, and we have to find the path along which the center of mass moves. From this figure you check that the x coordinate, which is this distance, is equal to L cos theta, while the y coordinate, that is this distance, from this triangle you can check that it is L sin theta. This distance is L sin theta from this triangle. And squaring and adding, we get the relation for x and y. So this is the path along which x comma y, that is center of mass, moves, and it is equation of circle with center at origin and radius equal to L. So center of mass moves along the circle during the time when the contact is not broken. Now as soon as this A loses contact with the wall, the normal becomes 0. So we have to use this fact that normal is 0 at that point where A is breaking off the wall. So at that point the forces acting on the system will be the weight of the rod, that is mg, normal exerted by the ground, call it S, and this n will be 0. So all these forces will be vertical. So there is no horizontal force on the system when the rod is breaking off the wall. So at that point the forces on center of mass will be vertical forces, because all forces get transferred to the center of mass. So n being 0, so we can say that there is no force now on center of mass in horizontal direction. So therefore in horizontal direction the acceleration of center of mass should be 0. Now since center of mass is moving along a circle, it has two accelerations, omega square L and L alpha, and at the breaking point the acceleration in horizontal direction should be 0. Therefore the component of omega square L and L alpha along horizontal direction must be equal so that they cancel out. So we have a relation like this. Now we have to put the value of omega and alpha of rod as a function of theta so that we can find theta. To find omega we have to use energy equation. A point is moving downward like this. The lowest point you can call it B. B is moving along this direction. Now we know that if there is a fixed axis in a body along which the body is rotating, then velocity of any point is perpendicular to the distance joining that point to the axis. Similarly, that V2 is velocity of the point M, suppose. So V2 is perpendicular to the line joining M and axis. So axis is such a point which when connected to any point becomes radius, and velocity is then perpendicular to that radius. If we know velocities, the direction of velocities of 2 points, and we have to find the position of axis, what we can do, draw perpendiculars on velocities. So this is velocity, direction of velocity, draw a perpendicular line. This is direction of velocity, draw a line perpendicular, and the cutting point of these perpendiculars is the position of axis. So similarly I have drawn a line perpendicular to this velocity. Now I am going to draw a line perpendicular to this velocity. Now the cutting point is instantaneous axis. So this point is instantaneous axis. So this rod is rotating about this instantaneous axis at this instant, and a rectangle is formed, as you can see. So it's a rectangle. So rectangle is formed here, and the other diagonal is this, and these two diagonals cut each other at midpoint. So since the total length of rod is 2L, now it means then this length is L, this is L, this is L, and this is L. So If the rod is rotating with an angular velocity omega about the axis, its kinetic energy is half I omega square, where moment of inertia we can find like this. So moment of inertia of rod about center, so this is ml square by 12, length is 2l, and plus shifting mass into shift, that is L, is square. So this is total moment of inertia about instantaneous axis, which on solving is 4 by 3 ml square. Okay, so now we're going to write energy equation. So since center of mass was initially at a height of L here when rod was vertical, and suppose at the point where this A is breaking off the wall, the center of mass is at this position and the angle turn is theta, this theta and this theta will be same, then the vertical distance which center of mass descends, this distance will be equal to L minus L sine theta, because this distance is L sine theta, this distance, this total length is L, so this is L bracket 1 minus sine theta. So using energy equation we can write the loss in potential energy, which is mg into L 1 minus sine theta. So this will convert into kinetic energy, and kinetic energy is half I omega square, where I is 4 by 3 ml square. So it is half I omega square. So this will give omega as a function of theta. So if we solve it, so omega from this equation we get is 3 by 2 2L 3g by 2L 1 minus sine theta. So this is the expression for omega square. And also we need alpha, which we can find by differentiating this equation. So 2 omega d omega by dt, that is alpha, as 3g by 2L, and it is cos theta into d theta by dt, that is omega, and omega will get cancelled. Okay, so this is the expression for alpha, which is 3g by 4L cos theta. So now we have to put the value of omega square and alpha into this equation. So we have now 3g by 2L 1 minus sine theta, this omega square cos theta, is equal to alpha is 3g by 4L and cos theta into sine theta. So this is the expression. Now we have to solve this. Cos theta gets cancelled. So we have 2 minus 2 sine theta is sine theta. So from here sine theta is 2 by 3. So this happens when sine theta is 2 by 3. So come into this figure. When sine theta is 2 by 3, then this height will be 2L sine theta. So it is 2L into 2 by 3. So which proves what we need to prove, that the top of the plank loses contact with the wall when it is at a 2/3 of initial height. So this height is 2/3 of initial height. Initial height was 2L. So at this height, the point A breaks up the wall. Okay.